Welcome to this presentation. Today, we'll be exploring problem number 1467, titled Probability of two boxes having the same number of distinct balls. This is a fascinating problem that involves probability and combinatorics. We'll discuss the problem, break down the approaches, and work through the solution together. Let's get started. In this problem, we are tasked with dividing n balls of k distinct types into two boxes. The number of balls of each type is given in the array balls, where balls, I, represents the count of the ith type. The division must ensure that each box has at least one ball. The objective is to calculate the probability that the two boxes end up with the same number of distinct ball types. For example, if one box contains two distinct types and the other also contains two distinct types, that would meet the condition. The input is in array balls, where each value is an integer between 1 and 6, and the output is a float representing the probability. Let's explore some examples to better understand this problem. Consider the first example with an input of balls equals 1, 1. Here, we have two types of balls, each with one ball. The only valid way to divide them is to place one ball of each type into each of the two boxes. This ensures that both boxes contain exactly one distinct type of ball, meeting the condition. Since there's only one possible way to achieve this, the probability is 1.0. Now, let's examine the next example, where the input is balls equals 2, 1. Here, we have two types of balls, two balls of type 1 and one ball of type 2. One possible way to divide them is by putting both balls of type 1 into one box and the single ball of type 2 into the other. In this case, both boxes would contain one distinct type of ball each. Another way to divide the balls in the balls equals 2, 1 example is to place one ball of type 1 and the ball of type 2 into the first box, and the remaining ball of type 1 into the second box. In this case, the first box would have two distinct types of balls, while the second box would only have one distinct type. A third valid division is to place the single ball of type 2 into the first box and both balls of type 1 into the second box. This results in each box containing one distinct type. Out of these three possible divisions, two result in the same number of distinct types for both boxes. Therefore, the probability is 2 out of 3, or approximately 0.6666666666666666. Now let's look at a more complex example where there are three types of balls. In the example balls equals 1, 2, 1, we have three types of balls, one ball of type 1, two balls of type 2, and one ball of type 3. One possible valid distribution is placing the ball of type 1 and one ball of type 2 into the first box, and the second ball of type 2 along with the ball of type 3 into the second box. This results in both boxes containing two distinct types of balls. However, most other valid divisions, such as grouping all balls of a certain type into one box, do not result in both boxes having the same number of distinct types. Upon enumerating all possible divisions, we find that only 1 out of 4 cases satisfies the condition. Therefore, the probability is 1/4, or 0.25. This brings us to the constraints and edge cases. This problem requires us to consider all valid distributions of balls while ensuring that both boxes contain at least one ball. Additionally, we need to calculate the probability that the two boxes have the same number of distinct types. The constraints ensure that the problem remains computationally feasible. There can be at most 8 types of balls, with each type containing between 1 and 6 balls, and the total number of balls is always even. Edge cases to consider include scenarios like the minimum input case, where the probability is trivially 1.0, or cases with all balls of one type, where a valid split is impossible. For larger inputs, where the number of combinations grows exponentially, efficient algorithms such as backtracking or dynamic programming will be essential to handle the computations effectively. To tackle this problem, we first considered a brute force approach. The intuition behind this method is straightforward: enumerate all possible ways to distribute the balls into two boxes and check whether the distributions meet the condition that both boxes have the same number of distinct ball types. To implement this, we would use recursion to allocate balls of each type to one of the two boxes. For every allocation, we would calculate the number of distinct types in each box to determine if the distribution is valid. However, the major drawback of this approach is its computational complexity. Since there are 2 to the power of k possible combinations of allocations, where k is the number of ball types, the time complexity grows exponentially, making it impractical for large inputs. As a result, while this method is conceptually simple, it's highly inefficient for larger values of k. To address these issues, we turn to an optimized recursive backtracking approach with pruning. Here, the core idea is to eliminate invalid states early in the recursion. By keeping track of the number of distinct ball types in each box as we progress, we can avoid exploring branches that cannot possibly satisfy the constraints. This makes the search process much more efficient while still using recursion to handle the combinatorial nature of the problem. The optimized recursive backtracking approach offers significant performance improvements over brute force by pruning unnecessary computations. While the worst-case time complexity remains exponential, pruning reduces the number of states we need to explore, making it far more efficient in practice. However, this approach requires careful implementation to ensure that all invalid states are pruned correctly. Another method we considered was dynamic programming, or DP. With DP, the problem can be reformulated into a state-based framework, where each state represents the allocation of balls of each type to the first box. A DP table would track whether a given allocation is valid and its associated probability. While this approach is elegant, its complexity arises from the growth of the state space, which depends on both the number of ball types, k, and the total number of balls. The memory requirements can become significant, especially for large inputs. In addition, implementing DP for this problem is non-trivial, as it involves managing a large state space and ensuring all transitions between states are correctly handled. While DP is conceptually powerful, its trade-offs in terms of complexity and memory make it less appealing compared to the recursive backtracking approach with pruning. Given the options, we ultimately selected the optimized recursive backtracking approach with pruning as our strategy because it offers the best balance between simplicity and efficiency. A few key observations led us to this decision. First, the problem constraint that both boxes must have the same number of distinct ball types naturally allows us to prune invalid states early, significantly reducing the search space. Second, the relationship between the total number of balls and their types aligns well with a recursive allocation process, making recursion a natural fit for the problem. Finally, probabilities can be dynamically computed during the recursion process, eliminating the need for post-processing and further streamlining the implementation. Compared to brute force, this approach is much faster while remaining relatively clear and straightforward to implement. And while dynamic programming might be more elegant in theory, recursive backtracking avoids the high memory requirements and complexity of managing a large DP table. That said, this approach is not without trade-offs. In the worst case, where pruning is minimal, the recursion still has exponential complexity. Additionally, careful handling of edge cases is essential, such as ensuring that both boxes always contain at least one ball. Despite these challenges, recursive backtracking with pruning is a practical and effective solution for this problem. To summarize, the chosen strategy combines the strengths of recursion and pruning to create an efficient and scalable solution for this combinatorial probability problem. By leveraging the constraints of the problem to prune invalid states early, we minimize computational overhead while still exploring all valid distributions. This approach strikes a balance between simplicity, efficiency, and practicality, making it well-suited to solving the problem within reasonable time and space limits. To solve this problem, we need to distribute balls of different types into two boxes in such a way that both boxes end up with the same number of distinct ball types. For example, if box A contains two types of balls and box B also contains two types, that would be considered valid. We measure distinct types by the variety of ball types in each box, not the number of balls themselves. The first step in our algorithm is to represent the input using an array called counts. Each element in this array represents the number of balls available for a specific type. For instance, if we have three types of balls and their counts are 2, 3, 1, it means there are 2 balls of type 1, 3 balls of type 2, and 1 ball of type 3. Once we have this representation, we generate all possible distributions of these balls between the two boxes. To achieve this, we use recursion to explore every combination. For each ball type, we decide how many balls to allocate to box A, and the remainder automatically goes to box B. This ensures that every possible distribution is considered, as long as the allocation for box A is a valid number between 0 and the total count of that ball type. This process is repeated for all ball types to explore every possible configuration. Once we have a mechanism to allocate balls between the two boxes, the next step is to track the distinct ball types in each box during this recursive process. To do this, we use two sets, SETA and set B. These sets are dynamically updated as we allocate balls. If any balls of a particular type are assigned to box A, that type is added to SETA. Similarly, if any balls of that type are allocated to box B, it is added to set B. By using sets, we ensure that duplicate allocations of the same ball type do not inflate the count of distinct types. After all ball types have been distributed, we need to check if the sizes of SETA and set B are equal. If they are, it means this particular distribution is valid, and we count it as such. To keep track of all valid distributions, a global counter is maintained, which is increment every time we find a valid configuration. Once the recursive process is complete, this counter will hold the total number of valid distributions, which becomes the final result. This approach hinges on a few key insights. First, the recursive exploration ensures that every possible allocation is considered, making the solution comprehensive. By iterating through all possible ways to distribute the balls, we leave no configuration unchecked. Second, the use of sets to track distinct ball types in each box is both intuitive and efficient. Sets inherently eliminate duplicate entries, allowing us to directly compare the number of unique types in box A and box B. Additionally, we can optimize this process further with pruning. If, during the recursive allocation, we encounter a situation where the current distribution can no longer lead to equal distinct types in both boxes, we can terminate that branch early, saving computational effort. In terms of data structures, the counts array allows us to efficiently access the number of balls for each type, while the set SETA and set B help us track distinct types dynamically. Regarding complexity, the algorithm's time complexity is exponential in the number of ball types because we consider all possible allocations for each type. Specifically, the number of states we explore is proportional to the product of counts I plus 1 for all ball types I. Space complexity, on the other hand, is governed by the recursion stack, which grows linearly with the number of ball types, or O(n). When implementing this algorithm, it's important to consider edge cases. For example, if all the balls belong to just one type, it's impossible to distribute them in a way that results in two boxes with the same number of distinct types, because one box would always end up empty of distinct types. Similarly, if the counts array is empty or all counts are 0, there are no balls to distribute, so the output should be 0. Another consideration is handling large counts of balls. The performance of the algorithm is more dependent on the number of ball types rather than the individual counts, as the recursion primarily explores different ways to allocate types rather than processing each individual ball. To illustrate the algorithm, let's look at an example with counts equals 2, 3. There are two types of balls, with counts of 2 and 3 respectively. Initially, we start with empty sets for box A and box B. For the first type, there are three possible allocations, 0, 1, or 2 balls to box A. The remaining balls automatically go to box B. Next, for the second type, we have four options, 0, 1, 2, or 3 balls to box A. Combining these allocations for both types, we generate all possible distributions. Finally, for each configuration, we check if the sizes of SETA and set B are equal. If they are, we add to our count of valid distributions. The final output is the total number of valid ways to distribute the balls. This solution solves the problem of determining the probability of distributing balls such that the number of distinct ball types in both boxes is equal. We first create a helper comb function to calculate combinations, which is essential for determining the number of ways to distribute balls. The main recursive function DFS, depth-first search, is used to explore all possible distributions of balls. It takes parameters such as the current index of the ball type being considered, the counts of balls in each box, and the number of distinct ball types in each box. For each ball type, the function iterates over all possible ways to distribute the balls of that type between the two boxes. The recursion stops when all ball types are processed, and the base case checks whether the number of distinct ball types and the total counts in both boxes are equal. The total number of valid ways to distribute the balls is then calculated through recursive calls. To compute the final probability, we divide the number of valid distributions by the total number of ways to distribute the balls, which is calculated using the combination formula. This approach ensures that all edge cases, such as unequal distributions or incorrect distinct counts, are handled. The use of recursion allows us to systematically explore all possible distributions, and the combination formula ensures that the solution is efficient and avoids redundant calculations. Here, we start by importing the necessary packages and defining our solution class. The core function, getProbability, first calculates the total number of balls by iterating through the input array. This array represents the number of balls of each color. Using this total, we compute the total number of permutations for splitting the balls evenly between two boxes. This is done using a helper method called combination, which calculates the number of ways to choose a subset of balls. Next, we use a depth-first search approach, implemented in the DFS method, to determine how many of these permutations result in the two boxes having the same number of distinct colors and balls. Finally, we return the probability by dividing the valid permutations by the total permutations, casting the result to a double for precision. The DFS method explores all possible distributions of the balls between two boxes, starting from the first color and moving through the array. For each color, we iterate through all possible ways to distribute its balls between the two boxes. The key here is to update the distinct color counts for each box. If at least one ball of a color goes into a box, the distinct count for that box increases. After distributing the balls of the current color, the method recursively calls itself for the next color. Once all colors have been processed, which happens when the index matches the length of the balls array, we check if the two boxes meet the conditions of having the same number of total balls and distinct colors. If they do, we count this permutation as valid. The method then aggregates the total number of valid ways by summing up the possibilities across all recursive calls. In addition to the depth-first search, we use two helper methods, combination and factorial. The combination method computes the binomial coefficient, which helps us calculate the number of ways to split the balls evenly. It uses the factorial method to perform the computation. The factorial method iteratively calculates the factorial of a given number by starting with 1 and multiplying through all integers up to the input value. This iterative approach ensures efficiency and avoids the overhead of recursion. With these helper methods, the solution is able to efficiently handle the mathematical operations required for probability calculations. To solve this problem, we use a recursive depth-first search, or DFS, approach. Initially, we start at index 0, representing the first color, with both box 1 and box 2 empty. Additionally, the count of balls and the number of distinct colors in each box are set to 0. The input array, balls equals 1, 1, tells us there are two colors, each with one ball. At index 0, we explore all possible ways to distribute the ball of the first color. The first option is to place 0 balls in box 1 and 1 ball in box 2. This results in box 2 having 1 ball of a distinct color, while box 1 remains empty. The second option is to place 1 ball in box 1 and 0 balls in box 2. This leads to box 1 containing 1 ball of a distinct color, while box 2 remains empty. For each of these choices, we proceed recursively to explore the distribution of the next color at index 1. Now, at index 1, we distribute the ball of the second color based on the states carried over from the previous step. For example, if the state was box 1 equals 0 and box 2 equals 1, placing the second ball entirely in box 2 results in box 2 having both balls, while box 1 remains empty. This creates a state where box 1 has 0 balls and box 2 has 2 balls, with box 2 containing 2 distinct colors. We repeat this process for all possible states, ensuring every distribution is considered. Once all the balls are distributed, we reach the base case, or index equals the length of the balls array. At this point, we check if both boxes have the same total number of balls and the same number of distinct colors. If this condition is satisfied, we calculate how many ways this particular distribution could occur using combinations. These valid ways are added to our total count. Finally, the probability is calculated by dividing the total valid ways by the total number of ways to split the balls equally between the two boxes. For this example, the probability turns out to be 1.0. In the second example, balls equals 2, 1, we again start with index 0 and explore all possible distributions. For the first color, which has 2 balls, there are 3 options. The first option is to place both balls in box 2, resulting in box 2 having 2 balls of one distinct color, while box 1 remains empty. The second option is to place one ball in each box, so both box 1 and box 2 have one ball and one distinct color each. The third option is to place both balls in box 1, leaving box 2 empty. For each of these scenarios, we move to index 1 and distribute the ball of the second color. This process continues recursively until all balls are distributed, and we evaluate the base case conditions. In this example, there are multiple valid distributions that satisfy the condition of equal total balls in equal distinct colors, such as placing one ball of each color in each box. By summing up the valid ways and dividing by the total possible distributions, we find the probability for this case is 4/7. For the third example, balls equals 2, 2, the process follows the same steps but involves more combinations. Since both colors have 2 balls, there are more possibilities for how the balls can be split between the 2 boxes. For instance, we could place both balls of a color in one box, or split them evenly between the 2 boxes. A valid distribution, for example, might involve each box containing one ball of each color, resulting in equal total balls in equal distinct colors. After exploring all possible distributions and checking the base case conditions, we calculate the total valid ways and the probability. In this case, the probability of the 2 boxes having the same number of distinct colors is 6/35. Now, let's analyze the time complexity of our DFS-based solution. Since we use a depth-first search with backtracking, the recursion depth corresponds to the number of ball types, which we denote as m. For each type of ball, we iterate over all possible ways to allocate that ball type between the 2 boxes. This gives us up to balls, index, plus 1 choices for each ball type, where balls, index, is the count of balls of that specific type. As a result, the total number of states the DFS explores depends on the product of all these choices across all ball types. Mathematically, this is expressed as the product, balls, 0, plus 1, asterisk, balls, 1, plus 1, asterisk, asterisk, balls, m1, plus 1. If we let n represent the total number of balls across all types, and assume for simplicity that each type has an equal count of n/m, then each term, balls, I, plus 1, becomes approximately n/m plus 1. This leads to a total time complexity of O, open parenthesis n divided by m plus 1 close parenthesis to the power of m, which grows exponentially with m. This exponential growth reflects the combinatorial nature of the problem, as we must explore all valid distributions of balls between the boxes. The time complexity also includes the cost of calculating combinations within the DFS. Specifically, at the DFS base case, we compute the binomial coefficient COM, count 1 plus count 2, count 1, which determines the number of ways to distribute the balls between the 2 boxes. This computation relies on factorials, and using the factorial formula, it takes O, count 1 plus count 2, time. Since count 1 plus count 2 equals n, this contributes O, n, to the time complexity of each base case. However, because the number of DFS states grows exponentially, this additional linear cost at the base case doesn't change the overall time complexity, which remains dominated by the exponential growth of states. Therefore, the final time complexity of the solution is O, open parenthesis n divided by m plus 1 close parenthesis to the power of m. Turning to space complexity, the primary factor is the recursion stack. Since the recursion depth corresponds to the number of ball types, which is m, and each recursive call consumes a constant amount of space for variables, the recursion stack requires O, m, space. This is the main contributor to the space complexity. Another aspect of space complexity comes from the combination calculations performed during the DFS. Specifically, the factorial computations for COM, count 1 plus count 2, count 1, may require intermediate storage for factorial values. If we use an iterative approach for these computations, the additional space required is proportional to O, n, where n is the total number of balls. However, because these intermediate values are not stored persistently across recursive calls, they do not contribute to the overall memory usage of the algorithm. Therefore, the overall space complexity is determined by the recursion stack, which dominates. This results in a total space complexity of O, m, where m is the number of ball types. Comparing this DFS-based solution to a naive brute force approach highlights its efficiency. A brute force method would generate all possible distributions of n balls into 2 boxes, resulting in 2 impossible distributions. In contrast, DFS with backtracking prunes invalid states early, avoiding unnecessary computations. While the DFS approach is more efficient, the exponential nature of the problem still leads to high computational costs for large inputs. Despite the optimizations introduced by the DFS-based solution, the computational complexity remains exponential due to the nature of the problem. In terms of best and worst cases, the solution performs better when the number of ball types, m, is small, or when the counts of balls are distributed unevenly among types, as this reduces the overall number of valid states to explore. On the other hand, the worst-case scenario occurs when m is large and the counts of balls are evenly distributed. In this case, the number of DFS states grows significantly, leading to the maximum computational cost. In conclusion, the DFS-based solution is a significant improvement over a naive brute force approach, as it leverages backtracking to avoid redundant computations. However, the underlying exponential growth in the number of states still makes this problem computationally expensive for large inputs. The final time complexity is O, open parenthesis n divided by m plus 1 close parenthesis to the power of m, and the space complexity is O, m, where n is the total number of balls and m is the number of ball types. This analysis highlights both the strengths and limitations of the DFS approach for tackling this complex combinatorial problem. When working on this problem, there are a few common mistakes to be mindful of. First, overlooking edge cases is a frequent issue. For example, scenarios where the input is empty or all the balls belong to the same type can easily break your solution if they're not explicitly handled. This happens because edge cases often expose hidden assumptions in your logic, which can lead to crashes or incorrect outputs. Another pitfall is relying on inefficient brute force solutions. Generating and evaluating all possible distributions might seem straightforward, but this approach quickly becomes computationally expensive for larger inputs, often leading to timeouts. Lastly, it's vital not to confuse the number of distinct types of balls with the total number of balls. The problem specifically asks for distinct types in some cases, and misunderstanding this distinction can result in entirely invalid solutions. Paying attention to these details is crucial for crafting a robust approach. Another mistake to watch out for is incorrectly updating the state during recursion. When using a recursive approach to explore different distributions, you must revert any changes you make. This process is called backtracking. Failing to do so can leave residual state contamination, which means one recursive call could interfere with another, leading to incorrect results. Additionally, ignoring constraints or optimization opportunities is a missed chance to streamline your solution. For instance, constraints like a fixed maximum number of types or counts can help prune the solution space, allowing you to avoid unnecessary computations. Leveraging these constraints effectively can save significant time and prevent your algorithm from exploring redundant or invalid configurations. Understanding how to approach this problem in an interview setting requires recognizing key patterns. For instance, the core challenge often involves combinatorics or subset sum patterns. A critical insight is figuring out how to split a set into two groups while maintaining specific constraints. Modular thinking is also extremely helpful, breaking the problem into smaller subproblems, such as calculating distinct types in a subset or generating valid partitions, can make the overall task more manageable. Optimization is another important strategy. Techniques like memoization in recursive solutions or leveraging mathematical properties, such as symmetry, can help reduce redundant work. Beyond solving the problem, clear communication is essential in interviews. Articulating your assumptions, edge cases, and thought process demonstrates structured thinking and can leave a positive impression, even if your solution isn't perfect. For practice, related problems like partition equals subset sum, partition decay equals some subsets, and target sum are excellent resources, as they share similar concepts of partitioning and optimizing subsets. Finally, let's consider alternative approaches to solving this problem. Recursive backtracking is often a go-to method because it's relatively easy to implement. However, it can be slow for larger inputs unless combined with optimizations like memoization to avoid redundant calculations. Dynamic programming is another powerful option, especially for larger inputs, as it leverages overlapping subproblems to improve efficiency. That said, it can be more complex to implement compared to backtracking. A combinatorial approach with preprocessing can also be effective in cases with specific constraints, like a fixed maximum number of distinct types. While this method is highly efficient for certain inputs, it might not generalize well to all scenarios. Lastly, greedy heuristics offer a fast option, but they usually don't guarantee correctness in all cases. This approach is best suited for approximations or when the problem constraints allow simpler solutions. Choosing the right approach depends on the problem requirements and the trade-offs you're willing to make. Great job following along. To wrap up, we reviewed the problem, discussed the brute force approach, and highlighted the importance of understanding combinatorics and probability in solving such problems. Don't forget to practice similar problems to strengthen your grasp of these concepts. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!